In this video, we're going to talk about the fundamental theorem of calculus, part one. There's two parts, but this is the fundamental theorem. It's like all of calculus kind of rotates around this one theorem. All right, so it's really important. All right, and we're going to cover it in multiple parts. So we've previously seen that integrals and derivatives are kind of opposite to each other. When we first introduced area under a curve, we had a velocity function. The area under the curve told us something about position. But we also know that if we take derivative of position, we get velocity. So kind of this area under the curve is the opposite of taking the derivative. Now we're going to explore that concept a little bit more. So before we do the fundamental theorem of calculus, we have to talk about something called an accumulation function. So we see the integral gives you how much you've accumulated. So if we looked at the area under the velocity function, that kind of gives you how far you traveled. All right, and this is the accumulation of distance or something like that. All right, if you're talking about a function that's about water leaking out of a jar, the integral, the area is going to give you how much water actually went out. All right, so this accumulation of change formula, all right, and this is a formula we've seen before, and it's going to kind of keep coming back up, is if I'm in my original function and I'm starting at A, I can get to f of b by adding the area under the derivative. All right, and again, an important thing whenever we're looking at this accumulation of change formula, we don't forget there's a derivative there. All right, but you're adding the integral of the derivative to get between two functions. For this reason, it makes sense to define a function that gives out how much you've accumulated up to a certain point. So we're really just defining a function just as this point. All right, what's kind of happening with our function as we're kind of going along to more x values. So an accumulation function is going to look like this. All right, just our normal function, but it's basically how far or how much we've accumulated starting at A and going to whatever our x value is. All right, so we'll do an example of this in a second, but it's called an accumulation function because your function is basically just giving you an area out as you progress. All right, so that g of x equaled -6 to x f of t dt. All right, f of x is shown in the picture, and certain given areas are shown. All right, evaluate the following. So the first one is g of -1. So first, let's just plug -1 in for x. This is the area from -6 to -1 of f t dt. And we know how to do things like this using areas. We're going from -6 to -1. That's this shaded region here. And if you don't hide it, that's a 12 under there. But remember, areas underneath the x-axis are negative. So our answer is -12. So when I plug in -1 into this g function, I get -12. Again, it's just the area starting at -6. What about g of 8? G of 8, same thing. All right, just plug in x into our function, which means an 8's just going to go there. All right, but this represents the area from -6 to 8. So we're doing this area, that area, and that area. So we're going to add all together these separate areas, and anything under the axis is negative. And that's 6 above, so it's positive. It is also negative, so it's -30 plus 6 is -24. All right, so this is an accumulation function. You can see I put in some number, and I just get the area up to that point. So I got the area up to -1, and I got the area up to 8. All right, so these are accumulation functions. All right, what happens when you take the derivative of an accumulation function? All right, and this is where the fundamental theorem is going to come in. All right, so here's the fundamental theorem of calculus, part 1. So we have this accumulation function, g of x. When we take its derivative, we basically, we're taking the derivative of our accumulation function. And when that happens, basically the derivative and the integral part cancel out, and my answer is just f of x. All right, so since integrals and derivatives are kind of opposites of each other, all right, when we do the derivative of this integral, they basically cancel out and we just get f of x. All right, so we're just taking this x and plugging it in for t. All right, it's really simple in practice, but really hard to remember. All right, so let's look at an example. And I already made a mistake. This should be a t because it's dt is the variable there. All right, so g of x equals the integral of 1 to x of 1 over t cubed plus 1. All right, what is g prime of x? All I have to do is just take this x and plug it in there. That's the answer. All right, so you see in practice, there's not actually a lot you have to do. You have to remember this kind of weird thing. You're taking the derivative of an integral. They cancel out. You just get basically the function that you had in here. All right, in this case, f of x is 1 to the square root of x of 1 over t dt. All right, so what we're going to do is we're going to find f prime of x. We just take this and put it in there. But here's where we have to remember some of our other derivative rules. Instead of just an x up here, we have an entire function square root of x. So we have to do the chain rule. So we did my first derivative, which was doing the fundamental theorem, and I need to multiply this by the derivative of the inside. And this is the thing that's inside of my accumulation function, because instead of just 1 to x, it's 1 to the square root of x. So I multiply this by the derivative of the square root of x, which is that. Simplify a bit. And that's my final answer. All right, so this one, the examples here just to show that you can do the chain rule with this fundamental theorem of calculus. All right, this one looks similar, but everything when we're doing these accumulation functions is like 1 to x. And this one's switched. We have the number at the top and the x's at the bottom. But we've learned that if you switch this around, I can just switch this the other way around. All I have to do is make it negative of what I had before. So if you ever want to switch the bounds of an integral around, you just have to put negative of the switch version. And now I can take the derivative. That negative I had to add is going to hang out. Then I'm going to put the x cubed in. Oops. All right, so I'm just putting x cubed in for t. All right, and because this is not just a single x as an x cubed, I need to multiply by the derivative of x cubed, which is 3x squared. All right, so just remember your chain rule and your integral rules. All right, it's a pretty simple process of putting in that top thing in for t, and then remember if you have to do the chain rule, doing the chain rule. All right, and this is the most complicated thing you could possibly have to do with this. All right, so generally it's just kind of like plugging something in to your t once you remember the fundamental theorem. All right, this one's a little bit harder because we normally have a number and an x, but here we have x's on the top and bottom. All right, so we can't really do the fundamental theorem unless one of them is a number. They can't both be x's, but here's what we're going to do. We're going to separate this. Think about, we can start at any number, but 0 is the easiest number to start at. And then I can go up to x and then up to 2x. So the area I actually care about is x to 2x. But I'm going to get that by using areas that start at 0. So I can go from 0 to x, and I can also go from 0 to 2x. And you see if you cancel out these two pieces here, you get left with the actual blue that I want. So let me just kind of write down what I mean. All right, here this is the same as the integral from 0 to 2x, that whole yellow part. And I subtract away that green part. And that is equal to the blue part I actually want. So I'm just rewriting this integral to only start at a number 0, but I have to separate it into two separate ones. And now I can do my derivative. The first one I plug 2x in, and I multiply by the derivative. And I subtract, I plug x in, and that's my final answer. All right, or you could simplify a bit. 2x cubed is going to be 8x cubed, 16x cubed, minus x cubed is 15x cubed. All right, so this one's just there to kind of show you that if you had x's on the top and bottom, you have to rewrite your expression in order to start at 0, and then you get your answer from there. All right, so here's one for you to try on your own, kind of the simplest case. I just find the derivative of this function. All right, I'll show you the answer in 3, 2, 1. All right, and that's the whole thing. All right, there's just an x here. So you just put it in for the t, and you're done. All right, so this one is kind of the simplest case versus the other more difficult cases we ended on. All right, so here are the important points of this lesson. Accumulation functions are functions defined as the integral of another function. When you take the derivative of an accumulation function, the two basically just cancel out, and you just get the function on the inside. And just don't forget the chain rule when you're doing this.